Okay, so we're in chapter 3 in the prime numbers. We started that last week, and this being an odd week, this is an even week, week 6. So I'm doing the tutorials this week, so I'll see half of you after this now for number theory tutorial. Just after this, and there we'll work on some of the chapter exercises that are here at the end of chapter 3. You go forwards here to pages 22. It's page 22. There's lots of nice, interesting looking problems there about prime numbers. So we'll investigate some of those in the tutorial. So I'd just like to very quickly, just in a couple of minutes, just point to what we did last time. Okay. So we defined prime numbers. Everybody knows what one is beforehand, but nevertheless, we got the definition again. So prime is a number, an integer bigger than 1, which only has 2 factors, itself and 1. There's the first few, 2, 3, 5, 7, 11, and the list goes on. The first thing we recorded about prime numbers was the fact that every integer factorizes into primes. So if it is a prime, well, it's already factored as itself, a product of 1 factor. If it isn't a prime, then by definition it's a composite, so it must factorize into a product of 2 other integers, and you just keep repeating the argument. If those first two integers that it factorizes into are prime, then you're finished. That's its prime factorization. Otherwise, you keep going. So you keep going, and eventually you keep factorizing a number. Eventually, you reach a product of factors, all of which are prime. They can't be factored any further. So that proof just drops out of the definition straight away. But what doesn't drop out is that fact that the list of prime factors you get at the end, you wonder about, is that unique? So starting off with any integer, could there be a different way of factorizing it? So there's many choices along the way, because a composite number will often factorize in a number of different ways. So if you make these different choices as you're factorizing the large number, who's to say that you mightn't end up with a different set of primes at the end, depending on the choices? Well, we were able to prove in the Fundamental Theorem of Arithmetic, we were able to prove that that's not the case. That every integer does factorize uniquely into primes. So here's 495 factorized into primes. It is the only way of factorizing 495 into primes. You might write down the numbers in a different order, but that's really just the same factorization. And a key tool we needed in the proof of that was Euclid's lemma. Euclid's lemma, which is a really nice property of primes and kind of lies at the bottom of a lot of the properties of primes that we're able to prove. It says that if a prime divides a product of numbers, then it must divide one of the numbers. Okay. So if P divides a product AB, then either P divides A or P divides B. And that fact allowed us to prove the fundamental theorem of arithmetic that prime factorizations are unique. So nearly finished the summary, but just the other thing to draw attention to, the other result we proved last time, which is really, really, really nice, and we'll kind of say more about it, or more on the theme of it later on today. But we looked at Euclid's proof that there are an infinite number of prime numbers. Okay. So we know that the sequence of primes begins 2, 3, 5, 7, 11. And I just put a dot, dot, dot. There's plenty more prime numbers. Well, not only are there plenty more, but the list of them never ends. Okay. There is no largest prime number. They keep on occurring. And we were able to prove that with a really, really beautifully simple argument, presented here as a proof by contradiction. I mean, it's so nice, you can even just go through it in a minute. It's a proof by contradiction, so you assume the thing is false. You assume there is only a finite number of primes. Here they all are, listed P1 up to Pn. Pn is the largest prime number. And then there's this little argument that says, well, if you multiply them all together and add 1, you get another integer, of course. And we've already said that every integer factorizes into primes. So this new integer, capital M, it has a prime factor. Of course, if we've assumed there's only a finite number of primes, any prime factor of M must be one of these P's that we've listed. So now we've got one of these P's which divides M, but of course it also appears somewhere in this product here, this first term. So P, we've got a prime that divides M and it divides this term, but then it must divide 1. Because if you're dividing M and you're dividing this first term, then you must divide the remainder as well. So you must divide 1. But of course that's a contradiction. You can't have a prime number dividing 1 because primes by definition are greater than 1. So it's a really nice proof by contradiction that says you can never list down all the primes in a finite list. Well, if I didn't have 1, I'd be looking at M and it would factorize into primes and I wouldn't be reaching a contradiction. So this is just it's a neat little device to produce an integer, all of whose primes factor, all of the prime factors of M are not contained in this list. So it's this neat little device that, given any list of primes, can produce another integer. So you multiply them all together, and then finally you just add 1 to the end. It produces a new integer that has whose prime factors of this new number, they aren't any of these because they are. But that's the point. That's what we're trying to prove. We're trying to prove the impossibility of listing all the primes. Because no matter what finite list you write down, here's a way to construct another number which has a prime factor which is not on that list by construction. So we added the one with the specific aim to reach this number which has a prime factor which is not on that list, in order to contradict the assumption we made at the start that these are all the prime numbers. That's how we prove there's an infinite number. So this is definitely a proof you need to appreciate, you need to understand. It's quite short, and once you do understand it, the penny drops, and it's a really, really, really appealing argument. Appealing because the ingredients used in it aren't, we've worked our way up to them already in these short few weeks. But the result is so nice and strong, saying there's an infinite number of prime numbers. Okay. You could also subtract 1 as well, I guess. It doesn't absolutely have to be a +1 that you use. You could use a -1. But there's some kind of device that you use that says that whatever finite list of primes you write down, there has to be more primes that aren't on that list. So therefore, the list of primes is unending. You can, so you can certainly get a feel for this. Now here's so let's take the first few prime numbers. So 2, 3, 5, 7, 11. Right, let's do this on the computer. We'll be waiting around forever if I'm going to. I'm going to demonstrate something which I think will help you understand that. If we take the first few prime numbers, 2, 3, 5, 7, 11, we multiply them all together, we add 1. So this is my number m. Okay, so it'll be a reasonably large number, 2,311. Maybe it might be a new prime itself. I don't know. we can factor n. This is going to spit out the prime factors of n. But now to understand the way the proof works is, can this number m have any of these numbers as one of its prime factors? No, it's can any of these be a factor of n? That's the question. And it isn't simply because they're prime numbers, it's because we've added on this one. So if one of these numbers did divide n, it would be forced, it would have to logically also be a divisor of 1. But it can't be, because a number bigger than 1 can't divide 1. Yeah, no, if I remove the, and it just simply tells me that the factors of m are that. This makes all the difference. When I add 1, okay, it just so happens to be exactly a prime number this time. That's maybe not that appealing. So I'll add on the next few, 13, 17. I want to get one that isn't actually a prime number itself. Okay, so there's. So this is the first few prime numbers up to 17. You multiply them together and add 1. You get this new integer, and it has certain prime factors. But then the argument, the proof, the way the proof works is, I don't have to actually calculate these and know what they are. The proof argues that whatever primes are going to appear here, they can't be any of the ones that you've listed first. Because if 90, if 11 did pop out as one of these prime numbers here, that would be a contradiction, because then 11 divides n, if it did come out here, but then it would also, 11 would have to divide 1, because 1 is equal to m minus this product, and this product has 11 in it. So it's impossible for any of these prime numbers to appear here in the factors of n. So, I mean, I did this originally because you raised the question, could you prove this by example, or could you illustrate this by example? Well, you can appreciate it by doing some examples like this. Taking whatever bunch of prime numbers, really, really long, multiplying them all together, add 1, factor the resulting number. The primes that come out of that factorization will be new primes. And that points to the impossibility of listing all the prime numbers in a finite list. You just can't do it. So, sorry? Because if you could list them in a finite list, then you just run this trick and this produces some new ones. But hang on, I just claimed I could list them all in a finite list. So it just proves that the list is unending of prime numbers. There's no end to it, an infinite number. Yeah. Yeah. So if you think of it, it's rather than a proof by contradiction, you can also think of it as a machine for producing new prime numbers. Yeah, but that doesn't prove it completely. This illustrates it. But it's more important, this process. You can think of this as a machine for producing new prime numbers. You feed in a bunch of new prime numbers at the top, and this produces new, fresh prime numbers at the bottom. And you can always do it. So the list of primes is unending. So whatever primes here, I just add these to I put those into the product, and then some fresh ones will come out. And I put those into the product, and some fresh ones will come out. And you just stay here forever doing that. Yeah. No end. Okay, so that's good. I mean, it's worth time. It's worth spending the time kind of meditating on that and thinking about it and appreciating it. Okay? It's a really nice classical argument in number 2. Okay. So we're going to describe some interesting things today. First of all, we give a special name to, so we have the special name of canonical form of an integer. So the canonical form of an integer is just when you express the integer in its prime factorization. So we have this kind of agreed a systematic way to write down the prime factorization of any integer. You write it down as some power of P1, some power of P2, etc. You can see all the prime factors of it here, and just to make it unique and unambiguous, you could say that the primes have to appear in increasing order, and they all have a integer exponent alpha I. So that's the canonical form of an integer, or just its prime factorization. So for an example, the canonical form of, what's the one in the notes, 495 is this 3 squared times 5 times 11. P1, the P2, the P3 that appear in 495. The exponent on 5 and 11 is 1, and the exponent on 3 is 2. And a lot of our argument, or a fair number of our arguments in number theory, are based on treating a number according to its canonical form, according to its prime factorization. Here's a interesting thing. We've talked a lot about the greatest common divisor and the least common multiple. And we had Euclid's algorithm for calculating the greatest common divisor, which also gives you an algorithm for calculating the least common multiple, because we proved, remember, that the product A times B is always equal to the product of GCD and the LCM. So if you know the GCD, you can work out the LCM and vice versa. So this exercise, it's asking us, if we know the canonical form, or if we know the prime factorization of the two numbers A and B, how do you relate those to the numbers GCD and LCM of A and B? Okay, so let's have a look at that now. So A has some canonical form, which is the product of all the i's. Use the same notation, I1 up to R, Pi, alpha I, and B. Is product I equals 1 up to S, Qi, beta I. Remember this pi, this is the product notation, just like we use capital sigma for sums, we're using capital pi for products. Works in the same way. This is exercise 3.1, page 20. So what we're looking for here is a similar product formula for GCD and maybe a similar product formula for the least common multiple. How to give a product type description of these, or a prime factorization type description of these, given that we know the prime factorizations of the inputs A and B. And the way we set it up here, the sets of primes P1 up to PR, so they're the ones appearing in A, and Q1 up to QS, they're the ones appearing in B. These are not necessarily, these are not necessarily the same. However, if we allow the indices, the exponents, to be greater than or equal to 0. So normally when we write down the canonical form, we just mention here the prime factors that divide into A. So the exponents are all at least 1. But if we loosen that a little bit and allow the exponents to be greater than 0, we can use a single set of primes So let's call these F. F1 up to Fn, say. Such that, so the set of F1 up to Fn is equal to the union of these two sets. P1 up to PR, union Q1 up to QS. So we just formed this set of primes, which is the union, two sets of prime factors of A and B. So then we can write the canonical form of A as a product from I equals 1 up to N of Fi alpha I. And the B is a product of I1 up to N of the Fi beta. This is just to get the two descriptions kind of matched together or similar. So A can be written as a product of these primes Fi. Each Fi has an exponent alpha I. Similarly, B can be written as a similar product with different exponents, perhaps. And each exponent is greater than or equal to 0. So the alpha I and the beta I are greater than or equal to 0. If any particular alpha is equal to 0, that means that that corresponding F does not divide A. Similarly, if one of these beta exponents is 0, it means that that corresponding F does not divide B. Well, now we can write the GCD of AB. It has a very nice description now. See, the GCD is the greatest common divisor of A and B. So it embodies the biggest number which divides into A and also divides into B. So the prime factor, now what I still have to complete here is the exponent. The prime factorization of the GCD of A and B, when you look at it, it has to be part of the prime factorization of A because it's the GCD of A and B divides into A. So its prime factorization of the GCD must be a subset of the prime factorization of A. But its greatest common divisor, also a B. The prime factorization of the GCD has to also be a subset, if you like, or part of the prime factorization of B. So what's the description of the ith exponent here in the prime factorization of the GCD? It must be the largest possible exponent that is part of the factorization of A and part of the prime factorization of B. So this is going to be the minimum of the corresponding alpha I and beta I. So you look at the two factorizations of the two numbers, you look for the primes that appear in both, and you take the smaller of the two exponents. Okay. We'll look at some examples now shortly. So you could even guess the similar result for the least common divisor. Just by a kind of symmetry argument, or what would we expect here for the exponent? For the greatest common divisor, we're seeing the minimum of the two exponents. For the least common multiple, not least common divisor, least common multiple, the LCM, we should see the maximum. See the maximum of the two groups. So this gives a nice description of how the GCD and the LCM of a pair of numbers, how their prime factorizations look in terms of the prime factorizations of A and B. Another way of thinking of it is that the prime factorization of the GCD is, if you like, the overlap of the two prime factorizations. What's common to both prime factorizations. And the prime factorization of the LCM is, if you like, the union of the two prime factorizations. Okay. And we'll look at some examples now on the computer. So we'll just get the computer to spit out, I'll give it some random pairs A and B. We'll look at their factorizations and look at the factorizations of the GCD and the LCM of that pair. We should see this pattern coming out when we look at this. Yeah. I'll skip the scans afterwards as normal. So let's go back to the computer on this. So we'll give ourselves an A, a random A. I make them large then. Landed one with a 6 and one with an 8, so they'll have a GCD of at least 2, so both even. D will be equal to the GCD of A and B. E will be equal to the LCM of A and B. So what we'll do is we'll look at, so we'll print out things in order. We'll look at A, B, D, and E. We'll look at the two numbers again. We'll look at the two numbers again, look at the GCD, the least common multiple, and then we'll look at the factorization, factorization of each number. Factor A, factor B, factor D, and factor E. Okay. So here's the original two numbers. I've given it two random numbers. The GCD is just 2. This is the least common multiple, even bigger number. But let's look at the prime factorization. So these are the prime factorizations of A and B. So we look at these prime factorization and we ask what is common to the both prime factorizations. Now these primes here appearing, they're all distinct primes. The only overlap is with the 2's. So there's 2 2's in A and there's 1 2 in B. That's the only thing that's common to both prime factorizations. So that means the prime factorization, so the second last number is the prime factorization of the GCD. It's just 2. Because 2 is the only overlap between these two prime factorizations. When we look at the prime factorization of the least common multiple, okay, this big long prime factorization, but this is the smallest prime factorization that contains both the prime factorization of A and B. So have we got 2 squared here? Yes. Have we got 61 here? Yes. Have we got whatever that is, 9 million, whatever? Yeah, there it is. Have we got 2? Yeah, we've already got some 2's. So we've already got 2's. 43, yes. 5519, yes. 523, 717, yes. Okay. So let's try another A and B that has a bigger let's go for this one. And it's going to be, in fact, when we're choosing random pairs, it's going to be, maybe I'll stick in by 35. Stick in okay, so I've marked, I added in some kind of commonality to so here's the original two numbers. They've got a GCD of 30, and this big number is their LCM. So here's the two prime factorizations of the original numbers. And here's the prime factorization of the GCD. The GCD is 2 by 3 by 5. 2 by 3 by 5 is the overlap of the original two prime factorizations. This one has 7 2's in it, this one has 1 2. So that gives 1 2 in the overlap. This one, the first one is 3 3s in it, and 1 3 is the second number, so 3 is the only number, is the only power of 3 that's counted out. And there's a 5 in both of them as well, so the 5 should be included. But none of the other prime numbers are included because none of the other prime factors appears in the other one. And the prime factorization of the least common multiple, this long prime factorization there, is the smallest prime factorization that contains both. Okay. When you look at every power of a prime appearing in A, it's also present in the LCM. And you look at every prime power appearing in B, it is also present in the LCM. And no other numbers are included in the factorization of the LCM. Okay. The GCD has a prime factorization, which is the largest prime factorization you can fit into both. And the LCM is the smallest prime factorization that includes the factorization of A and the factorization. So that gives us a nice relationship between canonical form and GCD and LCM. The word canonical just means a kind of a good description or a good, unique, standard description. So so a canonical form of something means a standard way of expressing something. So in this context, the canonical form of an integer, we're saying, is the prime factorization of the integer. A standard, informative, meaningful way of expressing something. And it's kind of unambiguous. It's a unique way of expressing any particular integer. So any particular integer, it has a unique prime factorization. It can't be expressed in two different prime factorizations. I mean, it appears outside mathematics with a similar meaning as well. Yeah. The canonical way of doing something would be the standard, agreed upon, perfect way of doing something. Yeah, special way. Yeah. Okay. You can also look here at let's see. Okay, so we can also here look at some other consequences that come out of the fundamental theorem, or specifically of the fundamental theorem in Euclid's lemma. You may have well seen this before, but the proof that root 2 is irrational kind of fits into this framework as well. And indeed, we can generalize this to the square root of any integer. So I hope you're aware, but if you aren't, you'll see it again here, that the square root of 2 is an irrational quantity. So that means it can't be expressed as a fraction of integers. So a rational number is any number that can be expressed as a fraction of integers, an integer A divided by an integer B. That's what a rational number is. And the square root of 2, which is a reasonable enough quantity, you draw a triangle with sides, a right angle triangle with the two short sides having length 1, and the hypotenuse will have length root 2. It's a very real quantity. You can construct it fairly easily. But it's not a rational number, so it can't be expressed as an A over B. Now this looks funny because I've written down here root 2 equals A over B. Well, that gives you the clue that this is a proof by contradiction. Well, the conclusion is that you can never do this, but it's a proof by contradiction. So I start off by assuming that you can do this. That's the way proof by contradictions work. So we assume that it is a rational number. Well, but maybe, I mean, you can tell I'm not claiming that because I've written suppose at the start. Yeah. And I haven't declared it's a proof by contradiction at the top, but I'm telling you, it's proof by contradiction. But anywhere you see a theorem that says you know, root 2 has a certain property, and then the first line is saying that it doesn't. Well, that's a proof by contradiction. So we assume what we're trying to prove is false, and then we're going to reach some kind of clear contradiction at the end. Not only do we assume that root 2 is rational, but we assume that this representation of the fraction is reduced as far as possible. So if the two numbers have a common factor above and below, well, you should go ahead and cancel that out of the fraction. So we assume that this representation, a divided by b, is reduced, so that a and b, in other words, are co-prime. They've got greatest common divisor 1. If they don't, then you should divide out by that factor to get smaller numbers, a and b, which are co-prime. Okay. So we can assume, we're assuming for the moment that root 2 is a rational number and that this representation, a divided by b, is reduced as much as you can. So a and b have no common factors. Well, if that's true, you can simply multiply both sides by b and square both sides. You then get this equation: b squared times 2 is equal to a squared. And this puts us back into the realm of number theory. So we now have a pure equation just referring to integers. It's not referring to fractions or square roots or anything anymore. This is, all the objects here are integers. So we're back in the subject of number theory, or the context of this unit. And okay, we consider this from a divisibility standpoint, from a divisibility point of view. And we see that one thing it's saying is that the number b divides a squared. Yeah. The left-hand side is a multiple of b, so must the right-hand side. Now there's two cases here. Either the number b is strictly bigger than 1 or it's equal to 1. If b is strictly bigger than 1, then the fundamental theorem of arithmetic says that you can factorize b into primes. So there's at least one prime number, p, such that p divides b. It could be that p is equal to b. B happens to be a prime number. But the FTA says that, well, b has prime factors. So we consider one of its prime factors, p. Now, p divides b. So by the transitivity of divisibility, p divides b, b divides a squared, so it must be the case that p divides a squared. Well, p is special. P is a prime number. And that lemma we proved before the fundamental theorem said that if you ever have a prime number dividing a product, it must divide one of the factors of the product. Okay? Because p can't be broken apart in a multiplicative way. So if it's dividing into a product, it must be that it divides at least one of the factors. Well, this is just a times a, so the conclusion we get is that p divides a. But now we're looking at a prime number p, which divides b and divides a. Well, that contradicts the fact that we claimed up here that a and b were co-prime. We seem to have arrived at a number p that divides both of them, which would say that the greatest common divisor is at least p. So that contradicts the fact. So if the b is bigger than 1, this number in the denominator is bigger than 1, then we get a contradiction straight away. So that can't happen. The only other special case is if b is equal to 1. That's a special case because 1 doesn't have any prime factors. 1 is like a special case. It doesn't have prime factors. But if b is equal to 1, then what the equation is saying is that a squared equals 2. Now, is that true? And remember, a is an integer. Is there any integer such that you square it, you get 2? Well, you can do a quick check. If you square 1, you get 1. If you square 2, you get 4. If you square 3, you get 9. If you square anything bigger than 2, you get something bigger. So we can just tell by inspection that there's no integer such that when you square it, you get 2. So that's a contradiction as well. So whichever way you look at it, if you assume that root 2 is equal to a over b, you get contradictions, no matter which case you consider. So therefore, it's impossible to write root 2 like this. So root 2 is not a rational number. And that argument, and it's left as an X